We can just get started. Okay, so let me just start for today. So today we're going to talk about Stirling numbers of the first kind. So this is basically the number of permutations of 1, 2, 3 to n. Basically n elements with k cycles. It's called an unsigned Stirling number of the first kind. So let's look at what this means. So if you recall from last time, this notation, it's cycle notation. It kind of meant that, 1 goes to 2, 2 goes to 3, and 3 goes to 1. And 4 goes to 5, 5 goes to 4. So that's a permutation of the numbers 1, 2, 3, 4, 5. So, you could draw it like this if you wanted to. It doesn't matter the order, but like of the numbers, locations, but yeah. So that represents that permutation. Another way you might write it was with the one line notation, which is basically 1 goes to 2, 2 goes to 3, 3 goes to 1. So you could write it like this as another way to write the same permutation. Okay, so here this is each one of these is called a cycle, and we need to figure out what are like the number of like. So let's just compute some small Stirling numbers of the first kind. So I'll use this notation to mean you have n numbers and there are k cycles. Another way to write it is with brackets. So this is a Stirling number of the first kind. And the reason I write unsigned is sometimes it's better to put a positive or negative sign in front of the number, but we won't talk about that today. So let's see. Can we compute some small values? So if we have a 0, 0, it's just defined to be 1. But if we have, I'll just use this notation. So this is defined to be 1. So, let's do an example. Like what would 4, 2 be? So how many ways can I put the numbers 1, 2, 3, 4 in a permutation where there's only 2 cycles? So, I'll let you think about it. So it's a permutation, not a, so you can't have, okay, I see. So you're saying, you know, there are two cycles and each number has two ways to go into them. But the thing is, like the order, it kind of matters. So like this is the same as this, right? Because this says 2 goes to 1 and 1 goes to 2. This says 1 goes to 2 and 2 goes to 1. Also, another thing, I guess that doesn't really matter. But if you have something like this, then there's only two ways to write this. I mean, this is different than this, right? Because this says 1 goes to 2, 2 goes to 3, and 3 goes to 1. This one says 1, you know, this goes in the opposite way around the 3 cycle. So you need to account for, yeah. Yeah, well, instead of casework on the number in the first cycle, how about the size of the first cycle? So, you know, we can have like a 3 cycle with a 1 cycle or 2 cycles. So, you know, how many ways are there to do the first way? Oh, okay, yeah. Yeah, you meant the size. Okay, gotcha. So how many ways can we do a 3 cycle with a 1 cycle? Not 4 times 6. So remember, like if I have something like 1, 2, 3, so there's it's the same as 2, 3, 1, which is the same as 3, 1, 2, right? This is all denoting the same 3 cycle. But the way we usually write it, like there are 2 standard ways to write it. One is just to put the smallest number at the left of each cycle. So I'll always write the smallest number at the left of each cycle. And I'll put the different cycles in increasing order. So like 1 is less than 4, and 1 is the smallest in its own cycle, and 4 is the smallest in its own cycle. Yeah, so there's 4 ways to choose. Yeah, it's 4 times 2 because there are 4 ways to choose what goes here, and 2 ways to permute the 3 cycle. So once I chose the number here, like let's say 3, then you can either go around the 3 cycle 1 clockwise or counterclockwise. 1, 1, 2, 4, or 1, 4, 2. Okay. What about if you have 2 2 cycles? Oh, so like the order of the cycles don't matter. So like this is the same as this. Like it represents the same permutation because this just says 1 goes to 2 and 3 and 4 swap with each other. This says the same thing. But I'll never write it the second way because like the standard way to write it is you put the smallest element. You order them by the smallest element. Yeah. Yeah. So you know, for Sid, you know, we're talking about Stirling numbers of the first kind today. So this is just how many ways can you put so I'm just going to type it. C and K is a Stirling number of the first kind. Unsigned Stirling number of the first kind. And it's how many ways to put, 1, 2, 3, 4, 5, 6, 7, like a permutation. Oops. 1 through n into k cycles. So another way you can think about this is like, let's say you have n people. They're numbered 1 through n. How many ways can you seat them at k indistinguishable tables so that oh, and these are circular tables so that no table is empty. So these tables, they like can rotate kind of. So like, if I have 3, 1, 4, it's the same as 1, 4, 3. So there are like j minus 1 factorial ways to seat the people around a j person table. Okay, so we're finding Stirling number 4, 2 for the first kind. Yeah, so instead of 6 ways, how many ways can I put them into two cycles? I mean, of 2 cycles of size 2. So if the tables were distinguishable, then it would be 6, but the 2 tables aren't distinguishable. So this would be the same as like this would be the same as this, because the tables are indistinguishable. So how many permutations of 1, 2, 3, 4 are in the format like A, B, C, D? Yeah, is it clear what the question is? So this just means A goes to B, B goes to A, and C and D swap with each other. So why isn't it 4 choose 2 equals 6? So remember, I said this was the same as if I put it like C, D, A, B. Yeah, the tables are indistinguishable. Yeah. So that means we need to divide this by 2, right? So there's actually only 3 ways. So no matter which cycle 1 is in, there's only 3 ways to pick the neighbor of 1, or like what 1 swaps with, 2, 3, or 4. And then the other 2 swap with each other. Okay, so there are 3 for this and 8 for that. So this number is 11. So, okay. Let's see. You know what? I think in the future for the next month, I might switch the class time away from Saturdays, because it seems like a few people have conflicts today, this Saturday in particular. But we'll see. it's summer, so maybe any day could be potentially bad, but yeah, I might switch it away from Saturday if there's enough people who want that. Okay, so anyways, so let's make a table of the Stirling numbers of the first kind. Let's say you have n and k. So 0, n is on the left. So this is defined to be 1. And then if these are all just zeros, because there's 0 people, if there are k cycles, if you have no cycles, that's not possible. So let's see, what would 1, 1 be? I don't know how to pronounce this, like how to say it out loud, but like Stirling number first kind 1, 1. Or the other notation is C of 1, 1. Let's just use C of 1, 1. Yeah. So this is just 1 because there's one person and there's always one cycle. Well, let's see if we can do something more interesting. Like what would n be? So C of n. Yeah, this is always 1 because if you have n people and there's n cycles, then every person maps to themselves. So the permutation is just the identity permutation, where P of I equals I for all I from 1 to n. So all of these are 1, and all of these are 0 since you can't have more cycles than the number of people. What about, let's see, what about n1? So C of n1. So how many ways can I let's say put 5 people all in one cycle. So maybe it's like 1, 2, 2, 2, 2. Instead of the alternative would be like 2 cycles or more cycles. This would be 2 cycles, how many ways can I get them all in one cycle? Well, so let's just try, for 2, 2, 1. There's just one way, I think. Yeah, they just swap with each other, right? For C of 3, 1, if you all have all 3 numbers in the same cycle, then you just have these 2, right? They either go clockwise or counterclockwise around the circular table. So this is just basically asking, how many ways can you sit n people around the circular table where rotations are kind of indistinguishable. So yeah, what should be the answer to this? Yeah, it's going to be 5 factorial over 5 for my example. And in general, it's n factorial, n minus 1 factorial, right? So this is 1 factorial, 2 factorial, 3 factorial, and 4 factorial. Okay. Maybe I'll just extend it another row. So what about, yeah, let me look at some of the questions that I had. Okay. What about what is C n minus 1? So this is like how many ways can I put 5 people in 4 cycles? Or n people in n-1 cycles? So if we do a smaller example, how many ways can I put 4 people in 3 cycles? Like, it would have to look like this, right? How many ways can I put them, like, you know, a lot of them C maps to itself, D maps to itself, and then A and B swap with each other. Yeah, feel free to whisper me an answer if you think you know. Well, so, you know, if you have, so the Drita says 2 times n-1 over 2. So that's almost right, but you're off by a factor of 2. So remember, you know, like, this is the same as the one I wrote right above it, right? Since it's the 2 numbers switching the same way with each other. So basically, it's just, okay, you have n-2 numbers that are, you know, mapped to themselves. And then the remaining 2, there's n choose 2 ways to pick them, right? So this is just n choose 2. There's n choose 2 ways to pick which 2 swap with each other, and all the rest just you know, stay fixed under the permutation. Okay, so if that's n choose 2, let's see. So this is 3 choose 2. This is 4 choose 2, 5 choose 2. Okay. We computed this was 11 for 4 elements into 2 cycles. Let's do like 1 or 2 more. So what about, is there some way we can compute 5 too? Yeah. So C5 too. So what are the cases this time? So let's see, we can have a number by itself. and then a 4 cycle. Or we can have a 2 cycle and a 3 cycle. So how many ways can we have the first case? And let me know if there are any questions, because you might not be used to the permutation notation yet or something. So it's not, so there's 5 numbers, right? Oh, I see how you're getting 6, right? So yeah, there's 5 ways to choose what number is by itself, and then 3 factorial ways to put the 4 numbers into a cycle. So it looks like 30. What about the second one? Is this even right? Okay, I guess that's right. Yeah, so treat this as 15 times 2. Let's see. So there's maybe a couple ways we can think about it. There's 5. Choose 2 ways for like which 2 are swapped with each other. That's called an involution or a transposition, I guess. It's not an involution, it's a transposition. And then there are, hang on. Oh, it's not 15 times 2, I think. It's there's 2 ways for the 3 cycles. So it's like 10 times 2 or 20. Okay, so that makes 50. Let's put that in our chart above. 50. What if we have 5 and 3? So if we have a C5, 3, let's see. So now there are, a few cases. What would be the cases for the sizes of the 3 cycles? Yeah, I think, yeah, they're non-empty, so it has to be 311 or 221, I think. Okay. So how many of the first type? Let's see. So for 311, how many ways? So it's not quite 5 times 4 times 2. I think you're off by a factor of 2. So yeah, the current question is how many permutations of 1, 2, 3, 4, 5, have 2 fixed points and the other one in a 3 cycle. Yeah, the single cycles are indistinguishable from each other. So there are 5 choose 2 ways to pick which 2 numbers map to themselves. So D goes to D, E goes to E under the permutation. And then the 3 cycle, there's 2 ways to put them, I think, because it can rotate A to B to C and then back to A, or A, C, B. So then that is 10 times 2 is 20. Okay, what if you have the other case? So now you have 5 elements, one of them is fixed, and then you have 2 cycles. So Daniel, right now we're doing Stirling numbers of the first kind, which is basically asking how many ways can I put 1, 2, 3, 4, 5, 6, 7, 8 to n into k indistinguishable cycles. So one interpretation is you have n people labeled 1 through n, and you seat them around k non-empty circular tables, where like if there's j people at a table, there's j factorial ways to sit them around a table, and each of the k tables is non-empty. You have to have one person or more, and the tables are indistinguishable. So let's see. Well, we can just, let's see, I can choose the fixed point in 5 different ways. And then I have 2 cycles, right? 2 length 2 cycles. So, wherever A is, there's 3 ways to choose the neighbor of A. So that's 15 ways. So 5 ways to choose which one's by itself. 3 you can think of as 4 choose 2 divided by 2, or just, one of the element has 3 possible choices for its neighbors. And then there's 2 choose 2 ways for the other 2 to be them, there's just one way for them to switch with each other to be a transposition. Okay, so we have 20 plus 15, which is 35. Okay. So maybe we should, get a recursive formula for this. Yeah. So maybe let's just do it in general. So let's say we want to do Stirling number of the first kind, C and K. So let's see. I'll just write it with the bracket notation. So unsigned Stirling numbers of the first kind. It's basically, there's this recursion. So let's see, how can we see this? So yeah, see if you can explain why this is true. It's similar to Pascal's identity with binomial coefficients. So what if, let's say n is this, so you have a permutation of 1 through n, right? What if n is by itself in its own cycle? So n maps to n under the permutation. Then how many ways can I rearrange the other n-1 numbers? Right, how many ways into like the cycles, right? So now there's k-1 cycles and there's n-1 numbers. So it's n c of n-1, k-1. So then what if n is not in its own cycle? So let's just take 5 or 6, like 5, 6 as an example, let's say. So let's say, I already have some permutation of 1 through n-1. I want to insert n, which is 6, into like some place, but it can't be by itself. So how many ways can I like insert 6 into the given permutation with n-1 elements? So I can insert it here. Yeah, so there are, C of n-1k ways to permute the n-1 numbers from 1 to n-1, and then the n by itself, let's see, n, it can be inserted right to the right of 1, to the right of 2, to the right of 3, to the right of 4, and to the right of 5, right? So you can either insert, so we have this cycle, and 6 can be inserted into any one of the 3 like slots here. And then you have a 2 cycle, and it can be inserted like here or right there. So there's n-1 ways to insert the 6, right? 5 ways to insert the 6. So there's n-1 in general ways to insert where the nth element is if it's not in its own cycle. Yeah, right. So notice here, with the permutation notation, you might think, oh, there are 4 ways to insert the 6, right? But, well, 2 of those are the same. Like, which 2 are the same? Let's see. If I inserted before the first one, and if I inserted after the last one, which is 3, these are the same, right? This 6 goes to 1, goes to 2, goes to 3, goes to 6. And this is the exact same cycle. 6 goes to 1, goes to 2, goes to 3, goes to 6. So yeah, you can only go to like, if you don't want to overcount this one, you should only insert it like to the right of every element, or always to the left of each number. I just go with right of each number. So yeah, this is true. So let's write down our table again and see if we can like compute, So we have, let's see. So this is 1 by convention. And if there's 0 people, then there's no ways. There's 1 way for like n people in n cycles. And there's n-1 factorial ways for, maybe we should summarize what we've learned so far. Oh, no, this is, hang on. Okay, I think this is what we had so far. So let's see, is this true? Like the thing was, so is this even true? Let's see, 50, it's 6 plus, it's 6 plus 4 times 11, 4 times this number. Yeah, that's true. 35 is 11 plus 4 times the 6. Yeah, that's true. Okay, it seems to be good so far. So this number should be 24 plus 5 times 50. Should be 24, so 274. This number should be 50 plus 5 times 1, the 35 right above it. So that's 175 to 25. I should just write it in black. And then this number should be 35 plus 5 times the number above it. So that's 85. Okay, so, are there any other patterns we can notice that we haven't noticed so far? Yeah, right. So we can see triangular numbers. That was this, we had triangular numbers here. So, that was the thing we already did, that was basically Cn, n minus 1, right? So you have n people and n minus 1 cycles. Then two numbers will go into a single cycle, and there's n choose 2 ways to put them in, right? So yeah, this number is always n choose 2. Any other things we can notice? So one thing that's interesting is, let's see, starting on row 2, like, is there a pattern called the quaternal numbers? What do you mean by that? I mean, there's square numbers. So, you have triangular numbers. These are triangular numbers, right? So you have 1, 3. 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 plus 4 is, so that's triangular. There's square numbers, 1, 4. Everyone knows square numbers. There's pentagonal numbers. So that would be like 1, 5, 12, and so on. I don't see, yeah. I mean, there's quaternions, but that's not really related to this. I mean, there's also Pascal's pyramid where you can have like trinomial, like, I don't know what they're called, but you can have like pyramidal numbers. But yeah, I don't see, because you can have like a pyramid with 1 in the first layer, 3 in the second layer, 6 in the third layer, and such, so on. And you can like make some sort of Pascal's pyramid with it. But I don't think I know anything about Pascal's triangle and quaternal numbers. Okay, so if we look at yeah, so one thing we can notice is like if I add up all the even terms in each row, starting at the second row, and it's equal to the sum of all the odd terms. So like 2 plus 1 is equal to 3. 6 plus 6 is equal to 11 plus 1. 24 plus 35 plus 1 is 50 plus 10, and so on. So basically what this seems to suggest is that, let's call this problem 6. Like the alternating sum is 0. So is there a way we can see that this might be true? This is pretty hard. So this is saying like, oh, 6 plus. So, I guess one way we can see this is, let's see where 2 has to be, right? So you have a permutation of 1 through n. So 2, if we write it in the canonical cycle notation, then so 2, it has to be like part of the cycle with 1, or since we're doing it like in increasing order, like like I'll always write it like here. This is the smallest element in its cycle. This is the smallest element in its cycle. This is the smallest element in its cycle. I'll always write it like, and then 1 is less than 3 is less than 4. So the smallest number in each cycle is the leftmost, and the leftmost terms are ordered from left to right. Like the smallest one is left of this one is left of that one. So not only is the smallest one the leftmost one in each cycle, but also the leftmost ones are in increasing order from left to right as well. So that's one way to write it. There's also another standard, which I won't talk about. So, you could have like either this be the case, and then, some other numbers, some other cycles, or you could have 1 be part of a cycle and 2 be part of another cycle. And then you have some other cycles. So there's only 2 cases. Either 2 is in the same cycle as 1, or 2 is not in the same cycle as 1. But suppose, the claim is, so here's the claim. We can like change each one of these into one of these and vice versa. So basically you just erase the parentheses that are here. So, you can get from case 1 to case 2 by simply, I'll just remove that parentheses. So A1 to AJ, and then, so if they're in the same cycle, you would just add the parentheses here. And then that would increase the number of cycles by 1, and you get a permutation with like 1 more cycle than originally you have. If they're in different cycles, then you just remove them. So if you start off with them in the different cycles, then you just kind of remove these green ones, and you'll get one with 1 fewer cycles. So that means all of the odd, if we add up all the odd numbered cycles, it's the same as like all the even numbered cycles. So that's why you can see that like 24 plus 35 plus 1 is equal to the 50 plus 10. Wait, maybe, yeah, that should be fine. So, the claim was just that the odd cycled ones are in 1-to-1 correspondence with like those with even cycles, like an even number of cycles. So yeah, the claim is basically number 6. Okay. There's one other interesting thing we can notice, which is, here's our table. I'll just not write in all the zeros. So the first row, let's see. So how should I state this? So, if we notice here, let's say I expand, like this corresponds to this. If I expand this, I'll get these as the coefficients. If I expand this, I'll get these as the coefficients. So, so this is called the rising factorial, where you kind of like go up. So this is this. If I write this, this is so 6. So we can kind of see that in general, the rising factorial is, let's see. I think something like that. So this is like, for instance, 3, 3. Well, let's just write it 3, 1, x plus 3, 2, x squared plus 3, 3, x cubed. And that corresponds to 2, 3, and 1. Okay, so, that seems interesting. And in fact, this is like an algebraic definition of the Stirling numbers of the first kind that are unsigned. Yeah, so I think, maybe we can come back to this. But for the second half of class, instead of doing more problems, are there any combinatorial topics that you guys would want to learn more about? Maybe I'll just do like a question and answer session. Because, yeah, I'm a little tired and. So, just, I guess there's some relationship between Stirling numbers of the second kind and first kind. Like last time, 2 times ago, we talked about Stirling numbers of the second kind. Today, was Stirling numbers of the first kind. There is some relationship between them, but yeah. Okay, so recursive functions. I guess we can do some recursion problems. That's fine. So let's take a 5-minute break and then we'll resume at 2:07. And then I'll decide what to do then. Okay. Uh, Ramsey's theorem. Okay, that sounds interesting. Yeah, that's fine. So yeah, there's a lot to be said about that. Uh, yeah, we might have covered it like at one point 1 year, but I don't remember. Let's see. Okay, so we can do a little bit about recursion in the intermediate class after we get into like counting and probability. So I'm not against doing that also in this class, but yeah, I think I'll hold off on that until maybe at least next week. So yeah, maybe let's talk about Ramsey's theorem. So there's like a few different versions of this, but like maybe the simplest example is like, what is, so, you know, the standard thing is there are 6 people in a room. And then we'll talk about extensions of this. Yeah. So let's just call the 6 people very uncreatively people number 1 through 6. So yeah. So yeah, how can we do this? It's kind of like a graph theory coloring problem. My voice is tired. Okay. So basically we have 6 points, right? They represent the 6 people and we put it on a graph. And then we connect, you know, this means like, oh, Daniel dropped. Okay, so green is no. Red is doesn't know. Hopefully Daniel can rejoin. Okay. So basically, we want to show that no matter how I color the graph, so maybe this is one color, right? No matter how I color the graph, there's always one red triangle or one green triangle. So yeah, how can we show this? Because if I have a green triangle, that's three people who all know each other pairwise. If I have a red triangle, that's three people who all don't know each other pairwise. So let's just look at an empty graph. Okay, so Drita says you can draw the first side and make sure that the hello, you can draw the first. So basically, what we're doing is like, if you have six people, then show that you no matter, so there's like 2 to the 6, choose 2 ways to color each edge red or blue, right, or red or green. So that's 2 to the 16th. I mean 15th, or this number. So that's a lot of different things we have to check, right? And for each one we need to check, is there always a red triangle or a green triangle? So Adrita says, oh, maybe we can like draw one of them and then check that, oh, at least one of these two makes a triangle with the first edge. So that's not a bad idea. So here, how about we do this though? So, if I just have one, let's say I look at the neighbors of one, right? Then by pigeonhole, there's 3 of one color coming out of person one, right? So without loss of generality, there's 3. I'll just say blue is, it's always done with blue. So we'll say green or blue means X knows Y, okay? So at least 3 of color coming out of person one by pigeonhole principle. So there's 5 neighbors of one, so 3 of them must be, half of 5 or greater than half of 5 of them should be one color, right? And then, so we could have all 5 neighbors be blue, or all 5 edges be blue, or all 4 of the edges be blue, or 3 of the edges be blue for the neighbors of one and its connections to its neighbors, right? So these are called the neighbors of one because they're connected by an edge. So then now what? How can I prove that there's always a red triangle or a blue triangle? let's look at persons 4, 5, and 6. What should be true about the edges between 4, 5, and 6? If I were to somehow avoid a blue triangle and a red triangle, what should be true here?
You can't attach 2, 3, 3, 4, 4, 5, or 5, 6 because that would give a blue or a red triangle.
Yeah, no matter how I color those, you'll get a blue or red triangle. So assume for the sake of contradiction, I'll just abbreviate for the sake of contradiction, there exists no red. The word is monochromatic, meaning the same color, monochromatic, or red or blue, monochromatic triangle. So this could be red or blue. Monochromatic just means same color, red or. So if we want to avoid a blue triangle, if any of these are, if any of these black edges are blue, then it'll make a blue triangle with 1. But if all 3 of them are not blue, meaning all 3 are red, then we have a red triangle. So we're done. So in the language of Ramsey theory, this means that R33 is 6. So what do I mean by that? So basically, like RKL is like the smallest number of like people, or of like the smallest n. So if this equals n, it's the smallest n such that, so it's, I'll just say the smallest number such that if you have this number of people, like this vertices of a complete graph, each edge of which is colored red or blue, each edge, I'll just type it, red or blue, RKL. Yeah, so it's basically, you're basically guaranteed to have, so in graph theory, Kn is the complete graph on n vertices. So K3 would be a triangle, K2 is just, 2 dots in a line. K4 would be, you draw 4 points and you draw all 4 choose 2 edges between them. K5 would be like you draw 5 points and all connections between pairs of the 5 points. So, this is K5, K4, K3, K2. So yeah, basically this number is the smallest number. It's the smallest integer, so that when you have this number of vertices on a graph and you draw and you color each edge red or blue, then you're guaranteed, no matter how you color it, to have a, let's say, red KK, so complete graph on K vertices, or a green KL, so a complete graph on like L vertices. So, maybe this could be like, so there's 2 things to check to find each of these numbers. One is that, if you have one fewer than this, can you find an example without this property? So, is there some way I can draw K5 so that I never have a red or blue triangle? How can I color the 10 edges here so that there's no red or blue triangle? Is there a way at all? So here's a thought. Does this work? There's no blue triangle so far, right? Is there any red triangles if I draw on the remaining as red? Yeah, there's no, right? Because this is just a pentagon, but like, you know, I mean, these aren't vertices. They just happen to cross, but they're not vertices. So yeah, there's no red or blue triangles. So that means R33 is at least 5, right? It's bigger than 5 because with 5, you can avoid having a red triangle and avoid having any blue triangles. And we just proved that R33 is at most 6, right? Because with 6, you're guaranteed to have a red or blue triangle by the pigeonhole principle argument we gave. So that means R33 is 6. So Ramsey's theorem just says that RKL exists, or, you know, one version of Ramsey's theorem is like, you know, let's say you have J colors, right? So this number exists for all like J tuplets of, you know, colors. So, you know, like we could have like R345. This just means what's the smallest number of vertices you need so that if every edge is colored like red, white, and blue, then you can avoid a white K3, a red K4, and a blue K5. I mean, like, what's the smallest number so that if you have that number, if you have this number, then you're guaranteed to have either a red K3, a white K4, or a blue K5. So that's what, you know, that means. You can have multiple colors, more than 2. So I should write that down. R345 means the smallest number of vertices, so that if each edge is colored red, white, or blue, then you are guaranteed to have a white K3 or a red K4 or a blue K5. So, and you can generalize to any number of colors. And Ramsey's theorem, one version of Ramsey's theorem is about this, and Ramsey theory in general is about this question, and how like no matter how many colors you are and no matter what these numbers actually are, this number always exists. It may be humongous, but no, it exists. So that's like Ramsey's theory, theorem. But let's just see if we can do this for like what's R3 for? So let's see. I think this might be like 9 or 10. Let's just try, figuring it out. So I think we can do the same argument. Like, let's say you have 1, 2, 3. Yeah. So either you have two cases, right? You could either have 3 red edges coming out of 1, at least 3 red edges. So this is red, and this will be blue. Or you have at least 6 blue edges coming out of 1, right? So in the first case, you if I color these green edges either red or blue, then either if at least one of them is red, it'll form a red K3 with 1, right? If all 3 of them are blue, then they'll just make a, oh no, that doesn't work. Hang on. Okay, we should look at this. We should look at these edges. So all the edges between these 6 vertices. Let's say, yeah, actually this argument might be a bit trickier than I thought. Let's see. So if we have six of the same color coming out of like, if I want a blue K4, oh wait, maybe this is fine. Maybe this number is 8. So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, right? So by the pigeonhole principle, there's like 4 of a color coming out of 1, right? And 3 of another. Or maybe 5 and 2 or 6 or 1, but at least 4 of one of the colors. So if all of these are, let's say we want a red K4 or a blue K3, right? So if any of these are a blue, then we're done. We have a blue K3. On the other hand, if all 6 of these are red, then we have a red K4, right? So then we're also done. So with 8 vertices, we can guarantee that we either have a red K4 or a blue K3, because by pigeonhole, each of these 7 neighbors of 1, 5, 6, 7, there's 4 of them that will be the same color connected to 1. And then we just look at these 4 and we can argue that one of these must exist. So maybe R3, 4 is 1. I mean, it's 8. For some reason, I thought it was 9 or 10. Wait, why does this seem a little off? Yeah, it's supposed to be 9. What's wrong with my argument here? I think I see. It's because okay. I think with 8, there's a counterexample actually. It looks like if we put them in a regular octagon shape, then supposedly if I connect all 2 neighbors and 3 neighbors, like maybe I'll do it in blue. And then the empty edges are red, then this is an example. So then 1, 3, 3, 3, 3, 3, 3, 3, 3, 3. So apparently this is a counterexample. So let's see, is there any blue K3? Well, no, there's only squares. Oh, hang on, I meant to do them in the same color, my bad. Yeah, these should all be blue. Let's see. So maybe we want to avoid a blue K4. Yeah, so no blue K4 and no red K3. So the reds, let's see, they are all the missing ones, which are these. And the longest diagonals. Yeah, so apparently that's a counterexample. So let's see, what was wrong with my argument from before? So with 8 people, 5, 6, 7, 8, let's see, you can either have, so if I want no K4s, okay. So let's say there's 4 blue edges coming out. Let's say like this. Then let's see, how do I color the things connecting these 4? So it looks like I can do this, 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 and then this, 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 and this, you have blue triangles, but no blue K4. Okay. So yeah, 8 people is not enough, but 9 people guarantees it, supposedly. So why does 9 people guarantee it? Let's see. So I think there's 2 cases. One is if I have 6 reds, right? 1, 2, 3, 4, 5, 6 reds coming out of one, then I don't want any red triangles, no red K3, so none of these can be red, right? So all of them have to be blue. if I'm going to avoid a red K3. But then if all of them are blue, then we have a blue K4. Okay, I think I'm mixing. We only need 4 of these, right? So let's say there's 4 neighbors of 1 that are red. Then, you know, if none of these are red, then they all have to be blue, and then we have a blue K4. So we're done. So that's if we have 4 or more reds coming out of 1. But if I have only 3 reds coming out of 1, then the others, the other neighbors, then that means there's like 5, 2, 3, 4, 5 that are blue coming out of 1, right? So 1, 2, 3, yeah. So we can't have any blue triangles among these, or it would make a blue K4 with 1. And we can't have any red triangles among these either. Hang on. This still feels like I'm missing something. So why can't I just like do the K5 like 1, 1, 2, 3, 4, 5, and then color the others blue. And then these can be blue. Like, why can't I just do like 2, 3, 4, 5, 6, 7, 8, 9? I don't see why I can't just color these blue and then these red. And then among those, I can have like a red pentagon. And so this will be 1, 2, 3, 4, 5. Yeah, I don't think there's a red K4 there. And then this can be like this. So there must be something in the connections between here that makes it fail. Let me just check something. So apparently there's an inequality which is like L is less than or equal to R K L minus 1 plus R K minus 1 L minus 1. So if this is 4, 3, this would be 3, 3, and this would be 4, 2. 4, 2 is probably just like, this is 6, this is that 4? Yeah, right. So you need 4 to guarantee, yeah, at least one red edge or a blue K4. Yeah, so apparently this is true. R4, 3 is less than that. I think there's a similar argument to the first argument we did with R3, 3. Yeah. So maybe let's come back to that. Like, one interesting thing to note is that like, I think R44 is like, I don't know, 18 or 17, and R55 is unknown. Like computers have not been able to compute R55. but it's between like 49 and 43. Yeah, so I think it's amazing that R55 is still unknown, because it doesn't seem like such a hard question for a computer to compute, but yeah, it's actually kind of hard. Because let's say there's like 45 vertices, right? So you have 45 choose 2 pairs of edges, and each of the 45 choose 2 edges can be red or blue. So there's 2 to that number of colorings. And then you can probably divide by some stuff because you're like off by a factor of 2 or 5 or something. Like you're off because you can like rotate the vertices around or whatever. But this is and then for each one of these graphs, you have to check, is there like a 5 vertices with all 5 choose 2 edges between them all red, or 5 vertices with all 5 choose 2 vertices between them all blue, which takes like it's not an immediately check among all of these edges, right? Because there's 45 choose 5 subsets of 5 vertices, and you have to check them for all of them. For all 5 subsets of 45 vertices, you need to check all of them. So a computer can't just do it instantaneously, but it's kind of amazing that it hasn't been done yet. Like people have not had enough computing power to compute the exact values. I think this might be 17, because this inequality says like it's less than 9 plus 9 minus 1. I think there's one other thing we can talk about is what's like R33. But yeah, are there any questions on something I've said so far? I think we can find this number as well. Maybe this is what I was thinking of when I I think this is 17. Let me just double check what R44 is. Let's see, R44. Yeah, this is 18. I think I was right on that. This is 18. Huh. But yeah, there was a famous quote by Paul Erdős, which said that it's pronounced like Erdős, kind of pronounced like that. But like basically, or at least I think he said it, like, if aliens come to destroy Earth and say, okay, well, if you tell us the value of like if you don't tell us the value of R55 or else we'll blow up the earth, then humans should like just combine all the computing powers like computers around the world and try to compute R55. But if they ask for R66 or the death of the earth as the only other alternative, then we should try to fight the aliens because R66 is like way too hard to compute. There's also Ramsey theory on the integers. Like there's also some other types of Ramsey theory, but I think basically they're basically like, can you have like, basically they kind of like say, okay, if a number is large enough, then you have to have some regularity among like certain patterns if you color everything like one of a few different colors. And that's what a lot of the Ramsey theories are about. Like I think another one is if you color the numbers 1, 2, 3, 4, 5, 6, 7, 8, can you color them in a way so that there's no 3 of the same color that are in arithmetic progression? And then same question if you have 9 numbers. So yeah, so can we do it? Like, can I avoid a 3-term like arithmetic progression, monochromatic arithmetic progression in the 1 through 8? Can anyone spot a way to color them red and blue? I think there's one way. Let's say I color it like this. Then there's no red arithmetic sequence of length 3. And then there's no blue arithmetic sequence of length 3 either, with any common difference. Okay, but with 9, I think it's not possible. And there's a nice proof of why, I think. So, I'm trying to remember how this one goes. But yeah, I think if you try, you'll find that you can't avoid any like, you can't avoid an arithmetic progression, I think. So let's just try like. Yeah, now this is an arithmetic progression. Oh, and the 258 is as well. So at the very least, this would be Ramsey theory on the integers. Ramsey Ramsey Theory. What happens if I copy this? Yeah, so. Yeah, there's another result that's this, but I'll just let you read it if you want. This is the Guo-Xue theorem. Yeah, but I think it's kind of like interesting exercises to find like R KL for small values of K and L. Like if one of them is 2, this is just saying, oh, like what should this be? Well, this says if this is a K2, so a red K2, that's just a single edge, that's red, right? And then this is a red KK. So if I have K vertices, either all K choose 2 edges are blue, in which case we have a blue KK, or at least one of them is red, in which case we have a red K2. So this is just K. So, this would equal this. So it's not really interesting unless each of the numbers is above 3. I think you can find some bounds on like, RKL. Like maybe they're like less than like 4 to the n and greater than. I think lower bounds are like not as, yeah, maybe you can find some upper and lower bounds. And that's been like done in the math literature already. But I think the best bound is actually like some binomial coefficient, like maybe something like this is an upper bound. And you can prove it with Pascal's identity and like one of the identities I wrote earlier, like this thing, I think. Yeah, but Ramsey theory is like a really cool area of research. My undergraduate advisor at MIT, I think he did research on that and related things and other things in combinatorics. But it's like one of the areas of math which is like very like there's not. I mean, I think there's a developing theory, but there's not really like a very extensive theory on like how you should prove what's a good way to get started proving unknown results. So maybe you can just like come up with something with no background on it. Whereas a lot of things in math, you need like so much background that, you need to study like, 5 years in graduate school to like even start to like do research on some open question in that field. So I think it's kind of a cool area to get into. I think the reason this one is 17 is because, like, let's say I have things numbered like oh, well, there's 1 and then there's 16 neighbors of 1, right? 1, 2, 3, 4. Pretend there's 16 neighbors. So then by pigeonhole, like now there's 3 colors, like let's say red, green, and blue. By pigeonhole, since 16, there's at least, 6 of them that are the same color. And, you could have 6, 5, 5, for instance. If you have 6 neighbors I'll just draw it up here. If you have 6 blue neighbors of 1, like neighbors that are connected by blue edges, then the remaining 6, you can't have any blue connections between them, or you'll have a blue K3. But then if all of these are red or green, then it becomes like, now it's just proving R33 with only 2 colors is 6. So if you have 6 vertices by the first thing we did, you're guaranteed to have a red triangle or a green triangle. So that means, 17 is enough to guarantee that you have, one of these, a monochromatic K3. I think to show that 16 is not enough is a bit trickier. Yeah. So that's kind of a cool proof that, at the very least, it's less than or equal to 17. And in fact, it equals 17, I think. Finding a graph that shows that the lower bound is 17 as well is not always super easy. Like it might take a lot of trial and error. Yeah, do you guys have any other questions? I think Ramsey theory is pretty cool to talk about. Do I have any problems on Ramsey theory? Yeah, I think I should make a handout on this actually. I don't have any like prepared, but I can definitely come up with some problems really quick after class and send them to you. Because I think this is it's really worth thinking about. It's definitely combinatorics and yeah, I can see if I can make some like basic problems that like outline what we talked about and extend them a bit. I think that would be really cool because yeah, this is like one of the coolest areas of math in my opinion. It's not super abstract, like it's very understandable, whereas like some things in math you have to have like you have to know linear algebra and group theory and ring theory and like commutative algebra on rings and like algebraic geometry, and there's just so much background, but this one is like very understandable, and there's like a lot of open questions that are very basic about this topic that are still open. Okay, so we'll just stop here for today. Thanks for asking the question, Daniel. I got to talk an hour about Ramsey theory. Yeah.
Thank you. Bye.
Okay, bye.